Unit 1, Looking Inside the Black Box. You can access this video and this review at www.srhschem.wikispaces.com. First question asks us to explain what Rutherford was able to determine about the structure of the atom from each part of his experiment. So the Rutherford gold foil experiment consisted of firing alpha particles at a thin layer of gold foil. Now, if we look up really extremely close and we just zoom in on one of these little atoms, we see that most of the time the alpha particles are flying straight through. So, although the vast majority of the particles pass straight through the foil, approximately 1 in 8,000 are deflected. So, in order for the alpha particles to pass through the atom has to be empty space with nothing to block the path of the alpha particles. So in the extreme close-up, we can see that the alpha particles that are passing through are the ones that aren't colliding with the nucleus, aren't running into anything, and are able to pass straight through. Some of the alpha particles bounced back. So about 1 in 8,000 are going to actually be deflected. So in order for them to bounce back, they must be ricocheting off of something that's very dense and very heavy. This object also has to be positive in order to deflect the positive alpha particles. So later, eventually, this dense positive object in the center of the atom becomes known as the nucleus, and it's made of protons and neutrons. So how is this inconsistent with plum pudding? So Rutherford was a student of Thomson, and he believed that the atom was the plum pudding model at the time that he did this experiment. So Thomson's plum pudding model just consists of a region of positive space with electrons bedded in. So this is just empty space that has a positive charge with some little electrons mixed in. So according to Thomson's plum pudding model, because it's pretty much all empty space, all of the alpha particles should fly through. We wouldn't get any deflection. But instead, we saw some of those alpha particles bounce back, so we knew that plum pudding couldn't be correct. So how should the plum pudding model of the atom be changed? So we need to go from the plum pudding model to what's known as the Rutherford model. So we have to add a dense positive nucleus. The evidence for this is that some of the alpha particles bounce back. The rest of the atom is going to be empty space. So the evidence for this is that most of the alpha particles fly straight through. Second one, complete the table below about the subatomic particles. So 3 subatomic particles, the proton, the neutron, and the electron. So the proton is positive and the neutron is neutral. These are both located in the nucleus of the atom. So this is that dense, heavy core that the alpha particles were deflecting off of. Electrons are orbiting the nucleus in an electron cloud, and they have a negative charge. So in our picture, we've got a spherical orbital with 2 electrons flying around inside. Next question is a table about isotopes. So in order to fill this out, first we need to know that in isotope notation, that the mass number is the top number and the atomic number is the bottom number. We could also write it as in a different notation. So for example, if we write cobalt 59, the element is cobalt and the mass number is the 59. So because I know it's cobalt, I could look up the atomic number and tell you how many protons, and the mass number is the sum of the protons plus the neutrons. So as far as atomic number goes, the atomic number is equal to the number of protons. So you can remember AP, atomic number, number protons. So the atomic number is the same thing as the number of protons. The mass number is going to be the sum of protons and neutrons. So most of the mass of the atom is in the nucleus, which is made of protons and neutrons. So whenever you think mass number, think of the big, massive particles that are in the nucleus. The charge is found by balancing the protons and the electrons. So if something has more protons than electrons, it's going to be positive. If we have more electrons than protons, it's going to be negative. So the quick way to do that is just to do the number of protons minus the number of electrons. We have minus electrons because they're negative. So first one that we have for letter A, we have hydrogen 3. So I know it's hydrogen because the symbol is H, the atomic number is 1. So I know the name is hydrogen just by looking at a table of elements. And the 3 comes from the mass number, which is the top number. So the number of protons is equal to the atomic number, so we also have 1 proton. Now to figure out the mass number, I'm going to have to just add up the protons and the neutrons. So we already know the mass number because it's given to us in the symbol. We've got 3, 1 hydrogen. So I know the mass number is 3. So if my mass number is 3, one of those particles is a proton, then I must have 2 neutrons because 1 plus 2 makes 3. To find the number of electrons, I see that my charge is 0. I'm neutral. So when an atom is neutral, it must be because electrons equals protons. So 1 proton minus 1 electron gives me a charge of 0. Next one, letter B, has cobalt 59. So I know because it says cobalt, I can look at my table of elements, find cobalt, and that's atomic number 27, which means that my protons is also going to be 27. The mass number is already given to us. It's cobalt 59. So the mass number in this case is 59, which means that my neutrons must be 32. So if I take my mass number, which is protons and neutrons, and I subtract out the protons, what I'm left with is neutrons. So if you do 27 plus 32, that's where you get 59. As far as the electrons, the charge is minus 1, and I have 27 protons. So I need to have, because it's negative, I'm going to have more electrons than protons. Since it's minus 1, I know I have 1 more electron than proton. So if you do 27 minus 28, 27 protons minus 28 electrons, we end up with minus 1 as our charge. So last thing to do is just to write our symbol. So mass number on top, atomic number on bottom, and then the element symbol. Next, for isotope C, we're going to have the atomic number 1, which means that we have 1 proton. The mass number is also 1. So mass number is protons and neutrons. I already have 1 proton. Therefore, my number of neutrons must be 0. In this instance, we know that we don't have any electrons, but I do have 1 proton. So 1 minus 0 is positive 1. So 1 proton minus 0 electrons is a plus 1 charge. So because this is atomic number 1, I know that this is hydrogen and the mass number is 1. So it's hydrogen 1. So to write this as a symbol, mass number on top, atomic number on bottom, and then the symbol is H for hydrogen. Next one, isotope D, is going to have 27 protons because the atomic number is 27. The mass number is the sum of protons and neutrons. So if we do 27 and 66, that's where we get the 93. 27 protons plus 66 neutrons gives us 93. The charge is given to us as plus 1. So that means that I must have 1 more proton than I do electrons. So if I have 27 protons, I must have 26 electrons. So this is going to be cobalt again, We have 27 protons, which means that the atomic number is 27, so we've got cobalt. So in this case, we have cobalt 93. And to write that as a symbol, it would be 9327 cobalt. Okay, last one, E. So because I have 28 protons, I know that my atomic number is 28. My mass number is 62. Therefore, if I do the 62 minus the number of protons, I get the number of neutrons. So that's where the 34 comes from. In this case, we see that there are 2 more electrons than there are protons. So if I do 28 protons minus 30 electrons, I end up with a -2 charge. So I can look up on the table of elements, atomic number 28 is nickel, and the mass number is 62. So that's how I get nickel 62. And to write this in isotope notation, 62 is my mass number, my atomic number is 28, and this corresponds to nickel. So I write Ni. Number 4 asks us, of the table that we just completed, which letters are going to represent isotopes. So an isotope is going to be something that has the same number of protons, but a different number of neutrons, which is the same thing as saying the atomic number is the same, but the mass number is different. So they have to be the same element. So first, we've got hydrogen 1 and hydrogen 3. Because they're both hydrogen, they have the same number of protons. What's different, however, is the mass number, and this is due to a different number of neutrons. So in this case, A and C are going to be isotopes. In addition, we have cobalt 59 and cobalt 93. So because they're both cobalt, they have the same number of protons, the same atomic number, but their mass numbers differ, and this is again due to differing numbers of neutrons. Which represent cations. So a cation is something that is positively charged. So we see that the hydrogen and the cobalt, C and D, are positively charged, so those are cations. Anions have a negative charge. So the -1 for B and the -2 for E make those anions. In an isotope, the number of protons / atomic number is always the same, and both are correct because the number of protons is equal to the atomic number. But the number of neutrons / mass number varies, and those are both correct because the mass number is protons plus neutrons. Explain how to use the number of protons to identify an element. So the number of protons is the atomic number. So then if I just look up my atomic number on the table of elements, I can tell you what it is. So for example, if something has 8 protons, the atomic number is 8, I know that it must be oxygen. Next one, why are there different colors of light given off during a flame test? So in a flame test, we take metal atoms and we burn them in a flame. So according to the Bohr model of the atom, I've got a nucleus in the middle with my electrons traveling in energy levels around the nucleus. So in the flame test, when an electron absorbs energy, it's being supplied by the heat of the flame. So this causes the electron to jump up in energy level, but this is unstable. So we call this the excited state. So in order to regain our stability, this electron needs to re-emit that energy, and then it returns back down to the ground state. So whenever the electron re-emits that extra energy, a lot of times this energy is given off in the form of light. And depending on the magnitude of the energy difference, so the change in energy, that dictates how much energy the light has that's being released. So if it falls within the visible range, then we can see it with our eyes. If that transition is too large, we get an ultraviolet transition, something that we can't see. Or if that transition is too small, we get infrared, which we also can't see. So while falling down, that energy can be released as light, and the amount of light, the amount of energy released determines the color of that light. So an application of the Bohr model is bright line spectra. So every single element has its own unique fingerprint of light. So here we can see lithium, cadmium, strontium. They've got different fingerprints of light where that atom absorbs and releases energy. So I could take the light from, say, a star and analyze that light and determine what elements are being burned by that star. So the way that we want to do this, we need to compare the mixture to the known bright line spectra. So the way I do this is by highlighting. So I go along the lines that are in the mixture and I highlight any ones that match up. So I'm just going across here and I'm highlighting each of the lines in the mixture that matches with the other known samples. So once I do that, so I'm going to do that for every line, I end up with two elements that are completely highlighted. So for lithium, every one of lithium's 4 lines is highlighted. And for strontium, all of those 9 lines are highlighted. Now, a couple of them are sort of highlighted for cadmium, but we see that they're not all highlighted. So this mixture doesn't contain cadmium. So because the bright line spectra for lithium and strontium match the mixtures, these are the 2 elements that are found in the mixture. Number 9 is some conversion problems. So if I want to convert 56.36 liters into milliliters, I need to know how many milliliters are in a liter. So milli means 1,000 times smaller. So there's 1,000 milliliters in 1 liter. So in order to do this conversion, first thing I should do is take the number that I'm given and put it over 1. That 1 is just a placeholder. So let me draw my next line. Because I know the conversion factor, I can go from liters to milliliters in 1 step. So if I have liters on top, I want to put liters on bottom because liter divided by liter would cancel. I want to change into milliliters, so what I want to end up with needs to go on top. So liter divided by liter would cancel out, and the only unit left would be milliliters. So now I just got to fill in my numbers now that I know I've set it up properly. So there are 1,000 milliliters in 1 liter. So since the 1,000 is with ml in my conversion factor, keep the 1,000 with the ml. Keep the 1 with the L. So whenever I solve this, this is my answer. Next one asks us to take 200 centimeters into meters. So I need to know centi means 100 times smaller. So there's 100 centimeters in 1 meter. So just like before, first thing I'm going to do is write out the number that I'm given with units over 1. Next, I need to cancel centimeters. So centimeters needs to go on bottom. I'm trying to end up with meters, so that has to go on top. So centimeter will cancel centimeter. So in order to solve this, I just got to fill in my numbers. I know that 1 meter is 100 centimeters. So whenever I solve this, I get 2 meters. Now, whenever you solve these type of problems, you should always try to think, does this make sense? So for the first one, because milliliter is smaller than a liter, if I have 56 liters, that's going to be a whole lot of milliliters. So I expect a big number. In the case of taking centimeters into meters, well, I know that a centimeter is smaller than a meter. So if I have 200 centimeters, that's not going to be as many meters. That's going to be a smaller number. Number 10, calculate the average atomic mass of bromine. So there's 2 ways that you can solve these isotope problems. One way is to make the table. So first we've got two isotopes. There's isotope A in yellow and isotope B in green. So you should totally highlight these just so you don't mix up the percent and the mass. You want to keep that together for isotope A and keep it together for isotope B. So my percent abundance for isotope A is 50.69 and 49.31 for isotope B. So I need to take this percent abundance and write it as a decimal. So you can remember two ways. You can either just move the decimal over twice or divide by 100. So whenever I divide by 100, I get 0.5069 and 0.4931. Now I need to fill in the atomic mass for each isotope. So the yellow isotope has an atomic mass of 78.92 AMU, and the green isotope, isotope B, has a mass of 80.92. So I'm taking the weighted average of these two masses here. So I expect my answer to be somewhere in the vicinity of those two masses. So if you get something that's way off, then you know that you probably didn't move a decimal or missed a step somewhere. So now I got to take this decimal percent and multiply it by the atomic mass. So whenever I do that, I get two numbers, and then my very last step is to add these numbers up. So I get 79.9062 AMU. Now the great thing about this is that we know it's bromine. So we can check on the table of elements to see if we got it right. So our answer was 79.906. The answer on the table of elements is 79.904. So it's a little bit different because perhaps these numbers were rounded off. The numbers on the table of elements, maybe those were more exact, but we're very close. So we know that we did this right. Now my answer, 79.9062, is in the vicinity of the 78.9 and the 80.9. So that's another way that we can check to see if we did it right. Number 10, find the weighted average of the isotopes in the table. So let's do this the other way. So if you use the formula method, we've got isotope A, isotope B, and isotope C. So what I'm doing is I'm taking the decimal percent and multiplying it by the atomic mass. So 76.8% in decimal form is 0.768, and I'm multiplying that by the atomic mass. For isotope B, it's 0.315. For isotope C, it's 0.097. So be careful. You still have to move that decimal over two places. You're still dividing by 100. So I repeat this for each isotope. So if I had 5 isotopes, I'd have to do this 5 times. If I had 2 isotopes, I'd only do it twice. So we solve, and these are the numbers that we get. So then we need to add those all up. So we get 47.5023 AMU. Now we don't know what element this is. It doesn't say that it's one element or the other. So the only check that we have, I know that I'm doing the weighted average of 3 numbers, 46.9, 48.2, 51.3. So I expect my answer to be somewhere in the vicinity of those numbers. Now, isotope A has the highest percent abundance, which means that that mass is most heavily weighted in my weighted average. So I expect my answer to be the closest to that number, but probably a bit higher because isotope B and C are heavier than isotope A. So that's going to drive the average up a little bit from the mass of isotope A. Number 12 asks us to complete the table below. So I want electron configuration and the number of valence electrons. So I've got my little cut off table of elements so we can count our electrons and do our electron configuration. Electron configuration just shows us how the electrons are arranged in their energy levels and atomic orbitals. So first atom is sodium. So whenever we do electron configuration, we are always going to start with hydrogen. So hydrogen is 1s1. The next element would be helium, which is 1s2. Now, every time you get to the end of an energy level or you change to a different block, you're going to write down what you got. So far we have 1s2. Next, we come down to lithium. Lithium is 2s1, second energy level, spherical shaped, 1 electron in that energy level. Beryllium is 2s2. So now that we're at the end of the S block, I need to write down what I have so far. So now I'm going to scoot over to boron, which is now in the P block. So I'm still in the second energy level. This is the first element in the P block, so it's 2p1. Carbon would be 2p2, and so on and so forth. So 2p3, 2p4, 2p5, and then I get to neon, which is 2p6. Now I'm at the end of an energy level, so I need to write down what I have so far. We come down, and now we're at sodium. So sodium is 3s1. So now that I'm at sodium, I just have to write down what I have. So I have 3s1. So there's my electron configuration for sodium. Now to figure out the number of valence electrons, I want to look at the highest energy level. So in this case, the highest energy level is energy level 3, and it has 1 valence electron in that energy level. Now let's do oxygen. So just like before, we're going to start at the beginning with hydrogen. So hydrogen is 1s1. That's first energy level, spherical shaped orbital with 1 electron. Helium is 1s2. I'm at the end of an energy level, so I need to write down what I have. Next, I come down to lithium. So that's 2s1. Beryllium is 2s2. And I'm at the end of the S block, so I need to write it down. Now I come over to boron, which is 2p1, carbon is 2p2, nitrogen is 2p3, and finally at oxygen, 2p4. So there's my electron configuration. In order to figure out the valence, I need to look at the highest energy level. So my highest energy level is energy level 2, and it's split between s and p orbitals. So 4 of those valence electrons are in a p orbital, and 2 are in an s orbital. So that gives me a total of 6 valence electrons in the second energy level. Now let's do calcium plus 2. So just like normal, start with hydrogen, go over to helium. We got 1s2. Lithium, 2s1, beryllium, 2s2. I'm at the end of a S block, so I need to write down what I have. Go over to boron for the P block, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. I'm at the end of an energy level, so I need to write down what I have. Now I'm down at sodium, which is 3s1, magnesium, 3s2. So I am at the end of the S block, so I got to write down what I have, 3s2. So come over to aluminum. This is the P block now, but it's the third energy level. So 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. I'm at the end of an energy level, so I write it down. Now I'm at potassium, 4s1, and calcium, 4s2. So I've got the electron configuration for calcium, but I don't have plain old calcium. I have the calcium ion with a +2 charge. So if the charge is +2, I must have lost electrons. If you lose something negative like electrons, you become positive. So I'm going to have to backtrack. So if I lose 2 electrons, first I'm going to lose that 4s2 electron. Then I'm going to lose that 4s1 electron. So that's 2 electrons, which gives me my +2, which means that I don't need that 4s2. So because I have calcium +2, my highest energy level is energy level 3, and it has a full octet, 8 valence electrons. So this calcium ion has somehow gotten rid of a couple of electrons, so we end up with a closed valence shell with 8 electrons. Okay, last one is chloride. So start with hydrogen, 1s1, 1s2, write it down. 2s1, 2s2, I'm at the end of the S block, so I need to write it down. Come over to P block, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Now I'm at the end of the second energy level, so I write down what I have, come down to sodium. So 3s1, 3s2 at the end of the s block, so write it down. Now I'm in the p block, so 3p1, 2, 3, 4, and at 3p5, I find myself at chlorine. Now this isn't plain old chlorine. This is chloride, which means that it has a -1 charge. So to have a minus charge, it would have to gain a negative electron. So to have a negative charge, I've got to gain something negative. So if we add one more electron, this is going to give us the same electron configuration as argon. So instead of 3p5, because this has an extra electron, it's 3p6. So once again, my highest energy level is energy level 3. And by gaining an electron, now chlorine has a full octet. So this would be a closed shell. Just some test taking tips. This video will be posted on SRHS Chem and on YouTube channel LEFFELlabs. You can watch it as many times as you like, or if there were sections of this that were kind of sticky or that you struggled with, you could easily find other review videos, websites, other sources that review those specific topics. And very important, eat breakfast or lunch, whichever one you have before my class, and bring your calculator.